怎么嘞？星期十二哈，因为我不想你拜五还要做工，我也不要拜五做工。因为有时候课排在拜五，没有办法要放在拜五，所以尽量不要放在拜五啊，我们大家都可以休息。OK，um, so okay, let's address some problem that we left last time. So first problem was I think if A is a deformation retract of X, okay, then the inclusion map on pi 1, which is induced by the inclusion on the space, is actually surjective. And then that day, I drew a picture, annulus. So we got an X here, okay? And then we got the smaller circle in the annulus, let's call it A. Okay, so let's choose some deformation retract in this way. Okay, so what's deformation retract? You can think of it as a homotopy. Okay, a homotopy from the identity map to a retraction. For the retraction map here, I think it's pretty easy to construct. Okay, how would you construct a retraction map? You can send all the points along the line into the corresponding intersection of that line with the smaller A here. You know what I meant? So if you draw a line across like this, right? Okay. So all the point in the X, right, you can send to this point on your A. Okay? And similarly, on the other side, then you send to the antipolar point on this A. And then you can construct a homotopy between these two maps. Okay. So if you look at the loop, okay, in X, okay, under this deformation retract, right? What happened to this loop? How is it a loop? Okay, so you use your, as in the proof of this surjective here, so you apply your deformation retract to this point here, so you send it to A. Okay, so you could imagine that this loop actually looks like this. So let's say we go this direction, then your loops is just staying to, and then come back like that. Okay. So how do you get the loops and circle the whole A? Then? Maybe you can look for this kind of loops. Okay, then under the deformation retract, then this the bigger loop and circling A. Then under this deformation retract, it will be a non-trivial loop. And deformation must be our I mean that the stand out just the x minus a where it always maps to the boundary of a.他外面的都可以缩到里面去，还是一定要缩在里面。Oh, okay. I think you misunderstood my space there. This X is an annulus. So there's nothing inside A. A is empty, annulus. So A is, you can think of it as a X1. Yeah. Okay, so I think in this class, another thing very important is also when I took this kind of class, right? When the lecturer draw torus, those sphere, the first question come out in my mind was, is this field or not? Is this field up? Okay, usually it's not. Okay, usually it's not. Okay, usually. Yeah, usually it's not. Okay. Otherwise, you would think that, you see, if I have a torus, right? If I fill up the torus, what does it mean? S1 cross S1 just left with S1, right? So you get simple space. If you have a sphere, you fill out the sphere, also you get simple sphere.
So usually there's a hole there. Okay, so yeah, it's good to clarify it. And then the second question was asked by Eric, right? So any non-homeomorphic but homotopy equivalent space. Okay, well, we just start from the non-homotopy space that we know from general topology. Okay, namely the closed interval and the open interval. Okay. So if I want to show that it is a homotopy equivalent, what I need to do was I need to find a map between these two. Okay, so F and G such that FG is isotopic, no, sorry, homotopic to identity, and then GF is homotopic to identity, like that. Okay, not necessarily equal, but sorry? Yeah, we need to find it. We need to find it. So there exists, I just need to find one for you. So um, one thing I can do for G was I just take inclusion. I just include it in. I just send everything in between 0 to 1 to itself. Okay. This is inclusion. How about the other direction? Okay, F here. How about the other direction? Okay. So there's few things you could do, but I'm not sure other things works or not. But what we're gonna do was we just send X to half, which is a constant map. So in this way, if you compose in two different ways, what do you get? You include open interval and then everything sent to half. Or you send to half first and then you include half into half. So either way, you will get a constant map. Okay, either way, you get constant map. So FG is from where to where? From open interval to open interval. Okay, is a constant map. GF is also a constant map. Is there a way from a constant map to identity map? What do you think? Is there a homotopy like that? You think of a homotopy? Okay, so the homotopy you want to think about is try and construct for me. So let's pick one of them first. So H1 from 0, 1 cross those interval 0, 1 to 0, 1. Okay, so can you construct one? So between the identity map and these constant map. So you need to tell me where x comma t go. Okay, the starting point is a constant map, and then the ending point is an identity map. Equals 0, only half. T equals 1 is x. How? Hydrogen. How, Adrian? Starting is half, ending is x. So how?
Yes, plus half 1.
Tx plus half time
1
1 minus t. Okay, so when t is 0, you get half. When t is 1, you get x. And then I think this is quite obviously continuous there. Okay, it's like polynomial. Polynomial are continuous. Okay. And then is every point live in open interval or not? It should be, right? And because these are just a number inside 0, 1. Okay, so you add them together, they are still inside. I think you won't jump out from 0, 1. Maybe you could check. You won't. Okay. Yeah. So it's the same, the same homotopy you can use for GF. Okay. Just change the domain. Okay. Yeah. Okay, but one thing to note here is even we have this homotopy equivalence property, right? But this open interval here is not deformation retract of the closed interval 0, 1. Okay.
So meaning there's no homotopy, okay, for you to have homotopy between identity on this closed interval to the retraction onto this space. There's no. Nothing. Okay, you can try and prove it in general, but one way to think about it is if you want to make this retraction, right, what could you do? You should send 0 and 1 to some place inside here. Actually, this will disrupt the continuity. Okay, because you have to go somewhere in between here. And then if you think about the loop that touches 0, that touches 1, what happens? When the point close to 0, still close to 0, but when you reach 0, suddenly the point jump. Yeah, but you can try and write down the general argument. The idea is like that. So, so it's not true that you have homotopy equivalent, then you have deformation retract. But it's always true that if you have a deformation retract, the two space will be homotopy. Okay.
So deformation retract is stronger. Yes. Sorry?
I think there is a property like a larger space that can deformation retract.
You mean okay? So you mean that these two are deformation retract of a larger space? Yeah. You mean can we always do that?
You have a proposition.
I don't think. Oh, yeah.
Good. Very good. Let's talk about that proposition as well. Because the past 2 days, I haven't uploaded my note exactly because of that proposition. I spent a long time digesting this proof here. Okay, I put a proof here actually. I don't left it as an exercise because I find it very non-trivial. So one way is very trivial. Yeah, one way is very trivial. The other way is non-trivial. Okay. So if you look at this proof, okay, this third space here is what we call a mapping cylinder. Okay, what we call a mapping cylinder here. So what's mapping cylinder here? So I define the mapping cylinder here. So given any continuous map, right, you can form this mapping cylinder. So you have a map, okay, and then you attach, you take the product between x and a unit interval, and then you glue with y, okay, take unit with y. But how you glue it? You glue the last bit of x plus I. What do I mean by last bit? So when time equals to 1, you glue all the x1, right, into fx. Okay. Can you imagine? So the picture is like this. So you have a x to y, right, like that. Okay. X to y. Okay. And then you have a mapping like that. F. Okay. But what you do is you cross x with a unit interval. Okay. And then you glue to f as in how you map into this f. So maybe this fx is a bit fancy here. Okay, so fx like that. Okay, this is the mapping cylinder.
Yeah. And so the point here is the cylinder here can deformation retract to x and deformation retract to y. Okay, so this requires proof. This proof is quite tedious. Yes.
Y actually. Y. You can do to fx and then do to y. Fx also can, y also can. Okay, yeah. fx also can, y also can. Actually, the proof pass through these three spaces.
Okay. Yeah. So one proof is this straight away go down to this image here is just y, and then to start from y to x, you can go from y. So yeah, so to go, you can go from where? Yeah, I cannot say like that. Oh. Yeah, I cannot say like that. Okay, the point is your ZF can deformation retract to this fx first, and then you go fx to x.
And this is what it digs in this proof. Okay or not? So imagine just now the two intervals.
You need to do this. So once you have an inclusion, and then you actually have this mapping statement. Okay, so meaning you view it as a deformation retract of a higher dimensional manifold. Can I use manifold now? You guys use the differential manifold. Okay, so manifold. Okay. So yeah, within the same dimension, you can't really see anything, but if you put them in a larger dimension, then something interesting.
Okay or not? Better. Okay. Yeah. Okay. Yeah. Okay. Yeah. So I also put some picture here. You can try and go through this proof here. Yeah. Very fun. Very fun. Actually, this proof require the homotopy equivalence property. Okay, you rely on the homotopy to help you build this to build this homotopy. Okay. Sponsor 好了，好了，做好了，多少钱？OK，太好了。Yeah，我觉得这个 Sam 我觉得这个 Sam，我觉得异常的顺利。I don't know why 啊，异常顺利。没有学生问我考试出什么。
那些会问的人又不想回答。
不是，问题是我有教 CST，问题是我有教 CST，但是那一班也感觉挺不错，我觉得挺好的。Yeah，谢谢。对，只是想告诉你，我最近蛮开心的。OK，Anyway，Yeah，OK，Okay. So I think we should resume talking about the free product. Okay. So let's talk about free product. So last time we stopped at this example here. Z2 cross free product with Z2 is not finite. Okay. Because A, I put a A, B here. Okay. So let's say this is A, this is B, right? So 1A start with 1B as infinite order. Okay. Remember the structure of this free product here was you are free to concatenate any word as long as it's not the identity element. Okay, and then if they are coming from the same group, we should reduce it. Okay, for example, this guy should be reduced to let's say 0B, but this is not reduced enough. We don't want the identity element, so you will get reduced to this again, and then this one will get reduced to nothing. Okay, is it? Yes. Okay, but imagine I can slip 1A and 1B alternatingly such that they cannot cancel each other, then this guy will be having infinite order. Okay, you won't get to the empty word. Okay, okay, so this is the difference between free group, free product and product. So can you see that in this free product space, there are different subgroup? I mean, you can realize the two Z2 as a subgroup of this group because you don't need to take product with the rest. Then you are your one of the group will be appearing as a subgroup of this free subgroup. Free product, sorry. Okay or not? So for example, 1A, 1B, this one. Okay, they will form a subgroup. Does it make sense? Z2 will form a subgroup inside this Z2 free product Z2. Okay, make sense? If it is product, then this is a bit different, or not? If it is product, then it is different. Okay, because you cannot just you can or you cannot yeah, this is not similar things. So I'm trying to say what's the difference here. So so let me put something, is finite. I'm trying to talk about the structure here. So instead of just 1 and 0, you would be getting other combination here. Okay, so you actually consider other combination instead of just 1 Z2 sitting inside the free product like that. Okay or not? Does it make sense? I mean, like, I don't think you can see this phenomenon here. Let me see. There is a Z2 here, but it's not the original Z2. Okay, there is a Z2 here. I think this is the Z2, right? Get this form of order 2 subgroup, but this one here is never either one of the Z2. This is another order 2 subgroup.
You mean 1, 0, and 0,
1, 0, 1. Yeah, unless you identify this 1, 0 as the element inside here. But 1, 0, Z2 only got 0, 1, where got 1, 0, 0, 1, 0, 0, 0. Cannot, right? Only isomorphic, but here it's not isomorphic, here is equal. Contain the sub as a subgroup. This is equal. It's not isomorphic. It's the real thing sitting inside here. So every group sit inside this free product as a subgroup. Not isomorphic subgroup, it's subgroup itself. Okay. Makes sense, So that's why we built this free product here. Okay, kind of a combination of free group and product group. Yes.
Why is that?
No. I didn't say it's better than free group. My point is better than product group. Better than product group. Meaning, better in what sense is contains all its factor, okay, as a subgroup. Does that make sense? Okay. Factors, okay, because it's a product, product inside got factors, so these are the factors. The G alpha is the factors. Okay. Does it make sense? Okay. So maybe I put here, although 1, 0, 0, maybe like 0, 1 also, and also 1, 1 form isomorphic Z2, but these are not in Z2. They only form isomorphic subgroup. It's not the real Z2. Okay, but on the other side is the real Z2. Okay, okay. Okay, so from here you can see that actually we keep the multiplication in A as well. We keep the multiplication in B as well. But the more thing we do is we artificially combine the multiplication between A and B just by combination. That's all. Yeah. Okay. Later will be useful for our loops composition. Okay. All right. So one actually can prove that. So there's one claim here. So how does this Z2 cross Z2 looks like? Free product. So actually this is isomorphic to something called the semi-direct product between Z and Z2. Okay. So I put a reference here. You can go and see what's called the semi-direct product. Okay, so you can look up this, but I can tell you some property about it. A semi-direct product by Keith Conrad. Okay, so who built out this Z and Z2? Leh? So for example, you can take 1A and 1B. Okay, free product together. And then the other side, you just pick one of them, 1A. Okay. So what's the difference between semi-direct product and product? So product, you just multiply components wise. Yeah. This one also multiply components wise, but not that easy. So meaning there's some contribution from the second component to the first component. You understand or not? So when you multiply these two components, second component, right? Maybe there's some effect on the first component that multiply. It's not just first two, the two component. I mean, the two elements for the first component multiply. There's some extra rule. It's a bit like multiplication. Okay, I suggest you to look this up in your history. But for now, we are not using it, so I was my end here. Okay. So how to see these actually? How to see this was because this is like isomorphism, right? I mean, like you should have a map, right? So basically, you can see from this map here. Okay, you can take the map from Z2 free product Z2 to Z2. Okay, so what's this map? You take the word here and then compute what's the length of this word. Mod 2. The length. So which one is in which one live inside the kernel? Live inside. Yeah. What's the kernel of this map? I mean, what's the kernel of this map? Mod 2 man. How you get 0? Even? Okay, you even length. How to get even length here? You just count how many letter inside your word. For example, this is length 2, right? And then this is length 4. Sure, yes. Okay, so we need to define length on reduced word. Okay, yeah. So after reduce is 0. Correct, true. Okay. So actually your kernel is generated by this Z. Okay. And then you suggest onto Z2. Okay, so this one mod out by Z is Z2. So then you can by first isomorphism theorem, right? So free product mod out by Z is Z2. And then how do we in A1, I think we didn't teach you how to recover your original group. Okay. So there's some form of product you need to take up, which is this semi-direct product. Okay, it's the most general. Okay. Maybe easy case is just product, but this case is not easy. Okay, so there's some other product we need to take. Okay, I won't define it for you, but you can look it up. Moreover, this is what we call an infinite dihedral groups. Okay, this is a groups of symmetry of the infinite tree. Okay, with a vertex at every integer. Okay, so this is a group of symmetry.
Does this
Yes.
mean that the it should be
Yeah, actually, yes. You mean, does this imply that? Yes. Yes, I think definitely, I guess. Yeah. Yeah. The other way around will need to require you to define the semi-derivative. So, I mean, if you have a quotient isomorphic to another group, and then you want to move, it's not like it's not like it's not like you just want to move the denominator across, multiply z on both sides. Take it. It's not that easy. Okay, so the multiplication in a group product is a product. So in this case, not the simple product, it's some extra. Yeah. Okay. And what do I want to say? Okay. So this is a symmetric group of this infinite vertex connected by edges. Okay. So you can think of this infinite generator as in translation. You can translate infinitely any times. And Z mod 2, what's the easy Z mod 2 symmetry here? Actually, it's just a reflection. Yeah, reflection. Yeah, reflection is a Z2 operation. Okay. Okay. So another nice thing about this free product is if you have G alpha, okay, include into our free product set here. Okay. Let's say all this G alpha has a map into another group H, then it will incur a unique map, okay, from this free product into H as well. Okay. I think this is pretty straightforward to define, right? So for example, I want to define phi bar on the free product of these group element here. Sorry. Okay, how do we define it? We know how to send each of them to H. So we just send them one by one and then multiply. Yeah, multiply because you are in H already. Okay, then you need to check all the homomorphism, whatever property that you need to check. Okay, to prove that it is a homomorphism. Okay or not? It's straightforward. Okay. I mean, the step maybe is not straightforward. You need to write down, but the idea should be clear. Okay, makes sense. So in this regard, it's like a product set. Correct or not? In this regard. Okay, similar to product set. Okay. Any questions so far? No? Question? Got? No? Okay, so well, one thing you can say was let's say the G include the G cross H and H include the G cross H. Okay, given these two inclusion, it implies that there exists a surjective homomorphism from the free group to free cross H. Okay. Sorry, I didn't write down the main point here. Subject. Yeah. Which one?
G cross H?
First one is free. Second one is just the normal product. Question? So this is a very important property I'm going to use later. Okay, next theorem. Finally, we reached the one of the milestone of this class is the Van Kampen's theorem. Kampen's theorem. Okay, this Van Kampen theorem is a little bit troublesome. Okay, but if you recall last time, what we did was I have a loops. Okay, I cover up my topological space with some AI open cover, such that their intersection is path connected, so that I can rewrite my loops into a product of loops inside each A alpha. Correct? Okay. But the point of Van Kampen's theorem was, can I do the same thing for homotopy or not? Can I do the same thing for homotopy or not? Okay, if I have homotopy between two paths, can I chop my homotopy to live inside one of the AL as a product of homotopy is in living in just one of the AL? Can we do that? Okay, so previously we was doing on the path, but now we want to do that kind of decomposition on homotopy of path. So this makes this argument very ugly. Yeah, very ugly. I won't spell out the full gory details, but I will try and motivate a bit. Okay, so first, similarly, you start with your X, okay, and then you cover with your A alpha. Okay, cover with your A alpha here, and then you want to make sure that okay, so there are two statements here. First statement here is for all alpha beta, if it is pairwise half connected, then the homomorphism phi from free product of pi 1 of A alpha to pi 1x, okay, is surjective. So what's this phi here? Okay, please remember this phi. This phi is very natural. If you look at this proof, if you look at this map, what's the first map you want to put here? A alpha is the inclusion to X, right? Okay, so you might think that this phi actually is just the map induced by the inclusion. Okay, it is that one. Okay, there's no special one here. So this is induced by inclusion. Let's call it J alpha now. Okay, previously we call it I, right? So for now we call it J. Later we'll use I again. It's surjective. Okay, so it's surjective. I think this is what we achieved last time. Okay, but in a different language. I just said as a product of loops in different AR. Actually, this is the free product space. Okay, live in the free product space. Okay or not? Does it make sense? Okay. Okay. Second, this one is very special. You could ask me why, but I won't answer yet. If for every triply intersection is half connected, okay. So the first step you got surjectivity, right? What's the next step you want? Plus injectivity. So you got the isomorphism. Okay. So what's inside that kernel? Okay. So what's in the kernel? Okay. So let me write down the result first. So we want our pi 1x to be isomorphic to this free product quotient by some n here. Okay, so what's this kernel? Okay, the kernel here is what? Is all the elements, okay, such that it is generated all this form. Yeah, all this form. Okay, then I draw like this. So I alpha beta omega, I beta alpha omega. Okay, such that this omega here live inside pi 1 of A alpha intersect A beta. Okay, and then what do you think what these I alpha beta B. So these are the inclusion. Okay. So why got two indexes? Because we are caring about the intersection between A alpha and A beta. So we include this into let's see. If alpha at the front, we include into alpha. Okay, beta at the front, we include into beta. Okay.
So technically, those two are different parts. Yeah, technically different, but it should be the same. Yeah, why is it technically different? Because you see, your space is a free product space. Okay, one of them I push it into A alpha, the other one I push it into A beta. So these two cannot combine one actually. A free product space cannot combine. Does it make sense or not? But if you view it as a loop itself, actually they cancel out. Cancel or not? Yeah, cancel. Because they are coming from the same. They are actually the same loop. But we purposely view it differently. One I push into A alpha, the other one I push into A beta. Yeah. So this is another technicality of this free productivity. Make sense? Does it make sense? 跟其他问可以问的 OK so far 可以接受什么过后再问 OK no problem OK so so then we have this okay so how to view this maybe I quickly draw some argument for you how we view this so if you look at A alpha intersect A beta right okay you have a map into A alpha and then the other map into A beta here so one alpha beta okay well you still can include it into to view the induced homomorphism phi okay so you can see what happened under phi here and then this will in terms induce map on pi 1 okay so this one become star so become pi 1 okay and then here star here here pi okay so under this commutative diagram here what did you know J alpha star I alpha beta star is equals to J beta star I beta alpha star okay these two are the same thing these two maps are the same okay in particular this tells you what I alpha beta star on some loop okay is equal to I beta alpha star on some other loops okay so if you rearrange this is exactly the kernel element correct or not I take inverse okay I take inverse okay so this is the kernel element so naturally these things are living inside the kernel but the problem is yes very good is this the only thing okay is this the only then this part will constitute the rest of the proof this part will constitute the rest of the proof and then that proof is very long very super long so the idea of that proof is maybe I don't tell you the details so just now the point is can you squeeze your homotopy okay into the product of homotopy just in A just in B okay just in any alpha A alpha you believe me or not you got any question okay you can read Hatchers it's very hard to read I got another proof from Oscar Randall Williams notes we only do it for two A alpha so meaning two open set Hatcher do it for more general open set okay you can try and compare these two arguments maybe it will help you to learn yes sorry this one because you already include the loops into It is just inclusion, right? It is just inclusion, then inclusion. Inclusion meaning is the original loops. You understand what I said, or not? So like inclusion. This is what inclusion means. I mean, you need to check what's the difference. I mean, you need to check the induced inclusion, but the usual inclusion is like, let's say I say include 0, 1 to like just now I say inclusion into closed interval, right? So let's say call this is I. So I of 0 is 0. So J alpha of that thing is that thing. I mean, you need to check out after induced. After being induced is still the inclusion. Inclusion meaning you send that thing to that thing. It's different from identity. Why? Because it's already close to identity, just that the space you started with is not the same space. Actually, inclusion and identity is the same kind of map. You send it to itself. But why we call it inclusion? Because you start with a smaller space. Okay. Yeah. Okay, so maybe I can show you some diagram that you could see from this proof. Okay, so there's some technicality you need to define first, and then we will try and break this homotopy into parts in covered by A, covered by B. Okay, some of them will be can live in intersection. Okay, so you can define it as A or B. Okay, and then next job is to make sure all your path live in A or live in B. Okay, do some conjugation actually. Okay, then you can you see you can split up your path like this. Okay, chop your path based on the chopping on the homotopy. Okay, yeah, and then you show that anything that sent to the constant path is actually homotopy to the constant path in the free product sense. Okay, so in the free product sense, meaning the homotopy have to work A alpha by A alpha. Okay, so altogether you have this. If you don't appreciate this proof for now, also can. You want to throw it away, also can. Okay, we're gonna use it only. Okay, for now. Yeah, yeah. If you think that you cannot understand it yet, you can just throw it away. But we have to know how to use it. 250. Yeah, can we do some example before we take a break? Let's do some example before we take a break. And then we'll start with another interesting topics called cell complex. Okay. Sorry. How many pages? I lost count already. Yeah. Our note is like super long for this course because there's a lot of detail for some of the proof. Okay, so we need to put it in. Is it? Okay, nice. Okay. Okay, so to talk about first example, we want to define what is called the wedge sum. Wedge sum come out in your assignment, So since I'm so late introducing this, right? Okay, so how about we just extend to Tuesday, okay? You can set earlier deadline for Monday. You're on there. We extend to Tuesday, but next week we still have also quiz go on. Okay. Yeah. But at the same time, I will come out with the next assignment as well. Okay, so you should start looking at it at least. Okay. Yeah. Does it make sense? Okay. Yeah. I won't delay in planning, but I can extend the deadline a bit. Okay. Right. So let's define wedge sum here. So we will talk about a bunch of topological space which is pointed. Okay. Or these pointed topological space. Okay. So what do you mean by pointed topological space? Do you have any idea, or have you approached the? Have you seen this kind of object before? Hmm?
Yeah. So although we call this wedge sum, inside your text file, it's not wedge. If you wedge inside your text file, it's like this. This is wedge. So wedge sum here is actually V. Okay, this notation is a V. Okay, if you're gonna type this way is Jinsen, huh? Okay, you're gonna type this V. Okay. So what we do was we take, oh, by the way, because Hang Wei, you not sure when you come back. So supposedly you are doing the duty this week for this week lecture now, but we're not sure you're coming back or not. So Jinsen take over yours. But Jinsen is next week. Do you think you can do it next week? Yeah, you can start already actually because I already put out most of the content, and then you can adjust after I put out the content. I actually put out my plan up to homology already. So you can try start and type. Okay. Okay. Yeah, and second chapter is not finished yet. But I have finished chapter 2 already. So I'm going into homology now. I mean my preparation. It's not your class, my preparation. Okay, so now we haven't finished chapter 1 yet. Hopefully we can finish on time. Okay. Right. Okay. So we take disjoint union. Okay, meaning they have no connection between each other. They are not subset of each other, and then we quotient out what at one point exactly at this pointed space. Okay. Do you know how to imagine this? So let's say I take a tattoo circle. Okay. I pointed, let's say these 2 points here. Then what I'm gonna do is I take these two disjoint union, and then I quotient the 2 pointed point, meaning I make those 2 points into a same point like that. Okay or not? That's it. So wedge product is like a point that connect. How do I say? I want to say something else, but let me organize it. There's something called a bouquet of flower. Okay, so someone called this a bouquet of flower. So let's say this one equals to 1. Let's say x1 like that. Can you imagine this space? Okay, people will call this a bouquet of flower. Okay, so there's infinitely many of them. You can give your girlfriend this one. Okay. Yeah. Okay or not? Okay. So this is 连在一个点. Yeah, so we glue them at a point. Okay, we glue them at a point. Huh? What? Because we're gonna compute some example based on this. Okay. Yeah. Huh? Any question? Yeah, I think I can make this a proposition actually. I think I'll make it proposition later. Sorry. The quotient here is just identify points. It's identifying points. Yes. It's a single point. Yeah. Yeah. So it's equivalent as gluing at that point. And we identify these points together. Huh? What do you mean by not much need? That's it. What kind of meaning? Okay, so this 1 point here was live inside every topological space, but other spaces in the topological spaces will belong to themselves. Away from that point, nothing changes. Acceptable. Now this is which.
Okay, how about let's compute some interesting example first, and then we will prove something on this wedge. Okay, how about just compute this wedge, the wedge of two circle here. Okay, what's the pi 1 of this guy? Pi 1 of this. So we call this a figure 8 space. Okay, last time we saw this as a deformation retract of someone, right? Okay. What's the pi 1 of this guy here? Okay, we're gonna use Van Kampen theorem to prove it. Okay, so to use Van Kampen theorem, you need to find some useful open cover first. Okay, you need to find some useful open cover. So let's say we choose this open cover. Okay, one is going like that, going a bit away. Okay. Okay, and then the other one will cover the other circle by intersect a little bit with the other one. Okay, so let's call one U, one V. Okay, so such that X is equals to U union V, like that, open cover. Right. So do you know what's U and V looks like? It's homotopic. It's homeomorphic to what? Okay, next one. Okay, and then how about U intersect V? Okay, just 1 point. So where they intersect, the intersection is looking something like this, X. Okay, so you can think of it as a retractable, yeah. But so let's call this X. Let me think. Oh yeah, you are right. Sure. So it's like this. So, cool. This detail is quite important actually. Whether you intersect tangentially or not. Okay, or transversely. Okay. So what's the Van Kampen theorem tells you? It tells you that pi 1 of X is equals to pi 1 of U, free product with pi 1 of V, okay, and then divided by N. So where is this N coming from? These are the, so let me write very small here. These are the loops in the intersection of U and V. Any loops inside there? Any loop inside there in our case? Trivial. Very good. You divide by trivial thing. So what's left is actually pi 1 U free product with pi 1 V, which is just x1 free product with Z free product with Z. Okay. So this is one of the group you will see in your assignment. Okay or not? Okay. Make sense? Okay. So you see in this case, this also differentiate between torus and this two wedge, right? Torus is Z cross Z, but this wedge product is a Z free product itself. So it differentiates between torus and this object. They're supposedly to be different, right? If I sell you a donut, you want this donut or the X1 cross X1 donut? All right, so this one is just like two loops put together. Okay, so it's different. Okay, so it's different. It's different where we put the two X1 together in particular. So this two X1 is like I just joined at one point. But the other X1 is like kind of like we also join at one point, but in different direction, and also we put a lot of X1 in one direction.
Yes，yeah，
对
x 等于后面的 figure x space，figure 是图 x 是8 space 是 space。OK， 啊，它像8吗？它不像8吗？你有8啊，现在可以 OK， I think it's better to stop for a while here. Okay, let's resume 313. 什么 motivation？哦，还没有这么早，还要进 cell complex 先才可以动到那个，没有这样早。
我以为这个 section 就
呃，我也是以为，但是我看一下，应该是后面还会用到 Kampen Theorem，所以 that's why 这是第一步，后面会用到，后面解释那个东西的时候会用到 Kampen。招生，我们 GT 难产了，你问 Eric，
我在改，你放心。没有，只是单纯你有80多个思路去那个还要加。
这样好像我在追他，现在已经是第3个位我要出一位，他想他突然要做 AM，然后结果
但加 solution 那个加了我半天考试。
对啊，就感觉加那个分就
你没提着solution 的作品啊？
不用我，但是有灵活都要加80个。
哦，
我觉得那个就放这吧。
没有，但是那些 solution 那个有些那个 C ref 不能直接加，它 label 移位。
我知道，我是说来，你就加那个 reference，
哦，
因为那个 big 不是已经做好了。
那个 solution 那个 feeling，
对啊，
反正你加一个项目，还有的他们就不用反光加，就是那种。
对啊，还有就是那些框我也处理一下，就是那些溢出来的框。
哦，我觉得暂时不用处理也不用紧，反正我们没有完整。
好像是手上都没有。
不是你前面也有。
也不是，我手里是还有一个问题，就是为什么有些是 chapter 的，有些是
因为我还没做完啊。
不是什么意思？你要把后面那个全部丢来前面
啊，对对对，
不用了，你都来不及啊，
我在后面
因为它分开
因为不是我分，是下面那个东西是他做的，我要把它全部移到前面的 link 去，不然我做 link 来干嘛？
啊，是
对，是我弄的，因为那时候要会有那种。
所以你稍微再给我一点点时间，好不好？我把这一点点小问题全部都 fix 了，我再给你一个完整的版本。如果你现在要一个 text file，我也可以。
你要多久？
我跟你讲，它一点点是无限，你知道吗？一点点是无限。
那我先把你想让我先加 reference。
对，因为 reference 的 bit 已经做好，因为如果就算交给下一个，然后他又不知道那个 bit 在干嘛，
所以 solution 不用移，
那个就不用管它去，
好吧？
哎，以后再看。
那 solution 我先保持现在这个样子。
可以啊，你 reference 先做好。
好吧，就是如果我们做东西，我们是不能用，但是看起来我应该多把东西，所以就搞做。
我还是觉得那个 solution 那个可能是好的，得改。算了，没
是啊，后面管他，就放在那边吧，能读。
那我做完 beaver，然后剩下的 maybe 我 for 好一杯。
现在自己可以整理了，后面就搞。
是啊，
肯定开学就一定开始忙了。
已经开始。
对呀、
忙了搞。
对呀、
就是你要我去忽悠我，
每个人一生做这个东西就有一段时间嘛。
就是我现在是有时间去做，但是如果有那个时间，我也可以做别的。
哎，所以你下个 Sam 打算好了要加 MA，
我不知道，想加 MA 或者 AA 吧。
我建议你加 MA，
为什么？
我想听。
好，
就你刚
啊，A 太简单。
因为他的 A 我听过，
就可以听到我的。你可以下个礼拜你就提早蹲点在这边，然后你看，Hello，
他们脑的 A，那2个在这里吧。
他也没拿过你的 A。
MA，因为拿 MA 就可以，我就不能加 A。
我想听你的，
我也很想再动那份动，我要再加
你很想弄那份东西，你还想要有个人帮你打那份，
也是可以。
因为你现在是你要给
我已经做到半个小时了。
半个小时，就是一个 chapter 里面的一半啊。
你可以把它标出来，然后让他们去找。
我不想，我知道这次交给你的，最后给我的感觉是我自己改的经历和我自己打的经历是差不多的，那还是我自己打的。
反正你们下个学期应该没有机会看到我，
为啥？
没有更深的课讲嘛。
所以可以来听你的，没有人肯定干活，反正下个赛不上你的课。
这个学期我们还有 ME，
三国下个部都是 M， 我要补这个两个
我还要拿过 ME 哦，
A 去年还没拿到，
懒，
第一期他们都跟我说会不用拿，
两对，
那可能我的 A 不得拿，然后可能拿个 B 就不要，另外一个再看。
理
我们要拿 PH 吗？我 Y。
哦，这样子，那个拿嘞，
对，我不是所有课都跟你一起拿的吗？你看我哪还有时间拿那个？所以这就是我一直吐槽我们学校的课应该靠本封闭的历史。
等这些已经准备好加线了嘛？
来 graph， 有 graph，
Combinatorics。
Theoretical physics, theoretical mechanics，
我想要听这个，
那有点不对，他们下面有拿 combined，
对，你给
应该不要拿名格系，这个 combined 对，看个 step， 因为我发现到这里 graph 的东西，
你在你的
啊，这个是一个
我就讲你那个 Y，
应该发现一个他这也是要用的手语，
或者你换一个方法写，你现在写了，跟下个 same 你就不写了啊，你看一个方法，我的学生也是这样子，他也是做我的，我也是做他们的一个，然后就现在工作看看，哎，里面彼得有讲到这个东西，哎，你可以的，我感觉有在听哪这边有大鱼。
大无语啊，靠对，你讲那种，
Hey Rachel, the 2409 student will be perfect. I still interested. Mahjong don't have.
2409
You know, PD go how many people? 6 only.
快你
And then
好啦，不然干嘛？
把那个麦克风放给不了。
you go to content. 对啊 ，LA 也
1到2个，不到2个人，
对啊 ，LA 也是没有。
1个到2个就好了，其他都不是的。
你没有去给那个麦克风用我学。
可是有没有新个就很多？
没有，一个是那一个班的人也就一个吧。
哦，
哇，他们都是你班的，其实。
别人追求
对啊，
是你，就我们班的过去
来
快点
哦，
这种
还有
我们班有些跟他不用我学的。
一堆人拿别人的，
那个是别人的。
有可能因为等下太轻松了。
那还在播那首歌，这种配乐，
他这首歌叫啥来着？我
我就说了，
做啊，
该有的，然后现在他不是 teams，然后就
他还没播那个自创歌，
下课时候
啊，你们在外面
他自创的，别人创的而已。
应该是他唱的歌。
那歌词是在你不要拿对。
哦，你是讲他给歌词给 AI，然后 AI 唱出来？哦，我就在想谁有出这首歌。I don't know. Ivan，金色，你知道 Ivan 在哪里吗？哦，在学啊，被金生推荐了。
他做的歌，
去哪里挖出来了？
他自己去了。
没有啦，是 YouTube 哎。
他放在哪里？我不出去。这个地方就是不用还钱的。
下个放我跟谁？
所以有人推劝退了。
好像有几个被骗
我靠！嘿，
哦，这样啊。那个名字很 real，但是你学起来都
surreal，很 surreal。
我送给他，直接在我们的群里面。
的 hell，
所以
哎，有翻译版的。
我的 hell，我的 hell，
你说的。
啊，对，在群里面。对，
讲错了，对啊。
我的 hell，
你这可以白热呀，这可以白热。
做成 TikTok 歌，它就 viral 了。放一点 video 啊，就 viral 了。我跟你讲，真的可以 viral 这首。Based on 我对那些 viral song 的理解。可以 viral，我觉得下马要出名啊。下马是不是也是要出名？嗯。他没有来，他没有。啊，
怪谁啊？
OK，
哦，
哦，
他就问我是不是一定要在米内同样是
不一定，
不一定
啊，你刚才讲不一定，
在看哪？
啊，
就掉血。
哦，
没有。
OK， right, okay, so actually as a proposition in general, what's in general? So in general, this map here, phi of pre-product alpha, pi1 of x alpha, go to pi1 of a wedge e alpha x alpha. It's an isomorphism actually. Okay. So y as the kernel n is trivial. Okay, assuming that each x alpha is half connected. Okay. Moreover, and also each x alpha here. So the small x alpha, the pointed point, okay, has an open neighborhood. Okay, u alpha in s alpha such that x alpha is a deformation retreat of this new open neighborhood here. A alpha equals to x alpha, wedge with b not equals to a u. Where?
Why you say that in trivial?
So assuming it's if this happen, then the above happen.
What's connected to?
Maybe something weird could happen. Yeah, something weird could happen. Okay, but the point here is exactly like what we did just now. We have X alpha, we plus a little bit of open set. Okay, we plus a little bit of open. Okay, and then if you have this kind of property happen, like what we did just now, those intersection will. You the在拍 video。
你外面跳。
OK， 放那首白人。怎么口气的极限？是我对你的思念。Okay. Right. So if you look at the intersection, then these intersections are just trivial. Okay. Then the n is trivial in particular. Let's try and prove this. You get yes, huh? 是吧 Little XL 在哪里啊 ？Has an open label U alpha. X alpha 啊 ，U alpha in X alpha 然后
前面那句不是有小 x？
哦，小 X alpha 是那个 X alpha 的 point base point。Yes, yes, 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 yes. Yes. Okay. This is a big this is a big one. This is a small one. Okay, in general, this could happen. So meaning if you deal with wedge product, right? If you deal with wedge sum, then you just take the free product. So this is the moral of the story. Okay, no need to care about n. But well, I mean, like other property, I think you need to be careful. Most of them is fine, but you need to be careful. You need to make sure your X alpha is path connected, and then the little S alpha has this kind of open neighborhood property. Okay, let's discuss two more examples. There's one example on graph one. I left it for you to study. I also put my own. I think it's coming from Hatcher. That's okay. I think that's okay. So let's go to the next example. 2. Okay. So let's talk about the complement of a single circle A. Okay. So talk about this complement here. So what's the pi one of this complement? Do you want to guess? Yeah. How many loops are there in here? In the complement. I think this is for the motivation examples, right? I gave you. If you still remember, I motivate the fundamental group. I let you play around the circle. Can be A1 plus A minus equal to A0, something like that. Okay. So another way to think about it is you can think of your R3 here. Can deformation retract to S2? Okay. This is not the empty S2. This is the filled up X2 already. Okay, or the V2. But you cannot pass through this ring, right? Okay, so the rest of the thing should maybe go something like this. Okay, the complement should look something like this. Make sense? Make sense? I mean, like you just take the ring away. Okay, but avocado, yeah, sure, avocado, yes. So, well, I mean, like you can split out this line here, this middle line here. Okay, you can split out this middle line, and then you can think of your complement like this. Okay, I think I draw it a bit ugly. So let me redraw it. Okay, so this line is coming from here. This is going here, and then this one go back in, and then this is the other side, and we have another one. But how do you think about this complement? There's a wedge way to think about this complement here. Okay, which is actually x1 wedge x2. Okay. Makes sense? Does it make sense? On wedge. Okay, so everything inside this S2, right? You can deformation retract to the boundary. Okay, everything outside can deformation retract to that boundary. Yeah. And these two are the homotopy type.
Yeah.
I think should be. Should be. Okay. So this is homotopy equivalent and not homeomorphism. Okay, homotopy equivalent now. So in this class, we will resolve to a weaker equivalence, homotopy equivalence. Okay, so that we can include more things than homeomorphism. Diffeomorphism is more restrictive. Your map have to be differentiable. Okay, homeomorphism is just continuous. Okay, now we even go to weaker one, homotopy. Okay, meaning when they compose, the continuous can compose, not necessarily equals to identity, but as long as there's homotopy. That's fine. Okay, so it's a weaker equivalence, but it's useful already, huh? Sorry, 年的点, here, right? This point here, this point. Correct or not? Oh, this is the wedge point. Makes sense. Okay. So in this case here, you can look at the pi 1 of this complement. What is it? It is pi 1 of x1 wedge x2, which is pi 1 of x1 free product with pi 1 of x2. But pi 1 of x2 we know is 0. Okay, so actually this is just z. Cannot. Yeah. So this is the way, like how we study nodes is also using this. Okay, we last studied the complement of nodes. Okay, if the complement of nodes have two different fundamental groups, then they could be different nodes. But if they have the same fundamental group, okay, are they the same node or not? Okay. I think we haven't solved it. Yeah. So it could be possible that two nodes, the complement of two nodes will give you the same fundamental group. Okay. Yeah. So this is an unknown in particular. This is an unknown. Okay. This is an unknown. How about the other knot? So how about this knot? This is two unlinked. Okay, so this is an unlinked. So how about this? Okay, let's say A, B here, unlinked. So what's the pi 1 of this complement? Okay, pi 1 of this complement. So you can think of your space deformation retract to this, okay. Is okay, and then similarly, all the rest will go into this big ball here. Okay. So in this case here, what we get is R3 slash A union B is x1 wedge x1 wedge x2 wedge x2. Okay, so in this case here, what's your pi 1? Let's call this x. Pi 1 of x is just z free product with z. Okay. So this is similar fundamental group as wedge x1 wedge x1, right? Makes sense, huh? Similar. Yeah. But actually, it's a different space, no? You need to realize what actually different space. So you see, pi 1 cannot see higher dimensional space already. I mean, pi 1 of this is z free product with z, right? Pi 1 of x1 wedge x1 also z free product with z. So pi 1 cannot recognize it. Pi 2 is a different case. Maybe pi 2 can recognize. No, we won't. I mean, like, depends. We have time at the last few weeks on it. Okay. Next, let's look at the last one. Complement of two linked circle. Okay, I think this one is also one of the examples we gave in the motivation. So this and then like this. Okay. So what's the complement of this? Can you imagine? Deformation retract to what? Well, the very big outside one should have a circle outside, right? How about the middle one? how do you deformation retract? Or maybe cannot deformation retract, you just find a homotopy equivalent. Okay, it's very interesting. How about think of this? Like that, and then you cover like that. What did you see? I think still can recognize, right? Maybe this one will be longer. Huh? Can you recognize? If let's say R3 throw away these 2 point A, B here. Okay, what is this? You have X2 outside, wedge something at the point, which is a torus. Okay or not? Okay, you see this pi 1 is different. Oh, what's this pi 1 here? Let's call this X again. Pi 1 of X is equals to pi 1 of X1 cross X1, because X2 is 0. X2 is 0. So this one is a set cross set. Okay. So you see, we can recognize unknot, unlink, and link using pi 1. They have different fundamental group. Make sense? Yeah. Okay, so we recognize. So this example is very important for the branch of knot theory. Instead of study the knot itself, okay, how they cross, how they intersect, we can study the complement of this knot. Okay, two-way approach to see the knot. Okay, maybe one is better than the other in one way. Any questions so far? I haven't shown you any non-trivial n, huh? I haven't managed to find any example. If you found any, you can let me know. I didn't show you any non-trivial n examples. Mostly now it's just wedge. It's the easiest thing you start with. Easier to calculate. Okay. Yeah. Okay. So let's go to the next subtopic, which is called the cell complexes. Actually, this is chapter 0, but I left it here because we're gonna use it now. So we're gonna define cell complexes inductively. Okay. Sometimes we call it cell complex, or sometimes we call it CW complex. Okay, so CW complex is an abbreviation for two properties. So first property is called the closure finiteness. Okay, later we will touch a little bit on this property. The other one, which I won't touch, you can see in the lecture appendix, is called the weak topology. Okay, so there's some topology you can put on the CW complex to make it a topological space. Okay, which we call a weak topology. Okay. So first of all, it is a topological space. Okay, constructed inductively. Okay. As follows. So how do you start? You start by a point. Okay, you start with a point. Okay, a few points could be few points or a discrete set. Okay, discrete set x0. Okay, so these are what we call the zero cells. Okay, with element zero cells. Okay. Then inductively, we will define what is called the n skeleton. Okay, so we're gonna have skeleton. So what's this n skeleton here? Well, we will attach the n cell. Okay, we will attach n minus 1 skeleton to n skeleton. Okay, by attaching the n cells. EAN via the what we call the attaching map. Okay, I will tell you what is this attaching map doing here. So basically, you need to glue your boundary of EAN, which is equivalent to xn minus 1 to xn minus 1. Okay, so let me draw it for a moment. So you have a zero cell like that, right? Okay. So what's one cell? One cell, you can think of it as a line or open interval actually. And you can think of it as a line or open interval. And then a two cell, how to draw two cell, yeah? Two cell, you can think of it as a open disk. Okay, two cell. And then three cell is like open disk, open cube, something like that. Yeah. Then how do we build this skeleton here? So first, maybe let's say we want to build X1 here. So X1 is a circle, right? Okay. So we could start with a zero cell. Okay. And then I attach one cell around this zero cell. Okay. So attaching map says what? You need to take the boundary. Okay, you need to take the boundary of this one cell here and glue it and then map it to the skeleton before it. So what's before one cell? It's a zero cell. Okay, so you need to tell me how you glue these two endpoints. Okay, I send it to this zero cell point. Okay, so that's why this attaching map is a gluing. You just need to glue the boundary. Okay or not? Make sense? Okay. Okay. There's different way to glue X1, you know. So I can also start with 2 points. Then I can take one cell, one of the one cell map to maybe zero cell A, and then the other boundary map to zero cell B. But this is not X1 again. So in this way, we actually need 2 zero cell. Okay, maybe like that. Make sense? Okay, huh? Okay, huh? Okay. So in the end, there's a gluing, right? Gluing in topology is what we call a quotient space. Okay, we actually are taking quotient. So in this case here, formally, what we had was the n skeleton is just the previous skeleton disjoint union with E alpha n, and then glue them. Okay, and then glue them. Okay, so these E alpha n actually are the open disk. Do we use this for open disk? Actually, we use B hall in our topology class. So let's use B lah. Open n disk. Okay. And we glue X and alpha phi alpha X. Okay, for all X in Xn minus. Okay, does this make sense or not? Let's check. Yeah, I think this is fine because X is a point, it's a boundary, and then image of this point is something inside the lower skeleton. Okay, I glue them together. I identify them as a point. Make sense? Okay, so for example, this one is X, right? And then the gluing attaching map here is like phi, maybe let's call this B lah, phi BX. Okay, I glue them. I glue it to A, for example. Okay, make sense, huh? If this step can stop at some n, okay, we will set our x to be x to the n. Then this n will become the dimension. Okay, this n will become the dimension of this space here. Cannot. So we will say that this, if this n stop, then x will be a finite dimensional CW complex. And the smallest of such n is called the dimension of this topological space. Make sense or not? Because what? This is also x to the 2, right? This is also, sorry, x to the 1. Okay, we just stop at 1. This one also stop at 1. Okay, yeah. So this is the dimension of this CW complex, one dimensional. Okay, this dimension also match up with your differential manifold notion of dimension because it's locally homeomorphic. Homeomorphic or diffeomorphic? What's your definition of manifold? Diffeomorphic? Locally diffeomorphic or homeomorphic? The most important definition of homeo, I think, just homeo is okay. Locally have to be homeomorphic to I. Okay, so if you work on this x1 is locally homeomorphic to R. So this is one dimension. Okay. And then we will say that this CW complex is finite if you just need finitely many cells to build it. So in this case, x1 is finite. Okay. You just need to use at least one 0 cell and one cell to build it. You can use more 0 cell and 1 cell, but doesn't matter. Okay. We will say that the CW complex is countable if it has only countably many cells. Yeah. And then before going to examples, let's define one more thing for this cell complex. We will define what is called the Euler characteristic. Okay, this generalizes the definition in graph theory. So we will only define for finite CW complex. Later you will see why we do this only because the Euler characteristic of this x here, let's call it chi x, is the alternating sum. Okay, alternating sum. This alternating sum depends on what is the n cell. N minus 1 to the n times number of n cell. Okay, so if you know about graph theory, what's the formula for Euler characteristic of a graph? Is a vertexes minus h plus faces. Okay, so vertex is a 0 cell, h is 1 cell, and then face is 2 cell. Okay, so this measure. Okay, if you imagine there's an infinite CW complex, then this will become a series. Is it possible? It could be possible. But I think those spaces could be too large. Yes. Or too much detail to study. But it's not impossible to study, I guess. Maybe you can build out a few from there. Maybe you can combine calculus 2 and algebraic infinite series. I don't know. Okay, here is just a finite sum. Okay. So let's look at some pretty nice example. It's like Lego. These things are like Lego. You build out the small pieces with the big pieces together, and then you form the space. In particular, there's one example in your textbook, which is the house with 2 rooms. And understand this house or not? Okay, so the textbook makes some calculation. Okay, I try to show you how to compute this. So basically, there are 29 points here, 29 0 7. Okay. And then if you count all the edges, it's like 51 of them. Okay, I already split up the 51 how to get them. And then also the faces, you need 23. Okay, so based on this, the left tree union here, you imagine what's the shape here. Imagine what's the real room happening here. Where is get covered, where is empty. Unfortunately, I didn't make this model. Can someone volunteer to make this for next week? Can someone help make this? House with 2 rooms. Okay. So you can see that the top piece covered everything except the entrance. Bottom is the same. Okay. And then the middle then, you kind of like make the 2 entrance open, but you could note that actually those 2 are not connected. Not connected. Why? Because of this 2 box here. Okay, so meaning if you enter from the bottom, you can only go to the 2nd floor. If you enter from the top, you only can go to the 1st floor. Very weird, or you can build one here. Ask IOI to build one. Townhouse. Townhouse, right? Townhouse is like this. The room, the door, you cannot go. Okay, there's a 3-story at the back of the mountain there. So you can buy 1.5 story. It's like about 60,000 like that. Okay, so you're gonna share 1.5 story with the other. Okay, those two persons will go get in by different door. So the 0.5 story you cannot reach to the other side. Maybe the sum can reach it. Okay, so this is the CW complex that constructed this example. But what's important in this example is this thing is contractible. Can you imagine how to contract? Meaning everything can contract to a point. The homotopy type of this CW complex is a point. Yeah. Yeah. Did I include here? No, I didn't include here. Why is it true? But I think yeah, you should go through the actual, see how he do the homotopy and how you homotopy. Very interesting examples. Okay, the Euler characteristic is 1 in this case. It's positive. Okay, how about sphere? Okay, Sn. How do you build sphere? Huh? Okay, how do you build sphere? I already built x1 for you just now. So x1 is like 1 point plus 1 cell. How about x2? How do you build this? You take a cloth and then identify the boundary of the cloth. So you need a point with a 2 cell. Okay, you need a point and a 2 cell. Okay, in general, you can do that for Sn. You need a 0 cell with a n cell. Okay, so where you identify the boundary of the n cell. So once you identify it, you need a point to glue it. So you need the 0 cell. Okay or not? Okay, so yeah. So how do we know that? Because how do we build Sn? Sn actually is a Dn quotient by the boundary of. Okay, and then next one is a real projective space. Again, we see this in algebraic geometry before, right? Okay, these are the, I think half of it you should very familiar with. Okay, for example, all lines through the origin in Rn plus 1 is Rpn, which is you just throw away the origin and then you identify them if they are on the same line. And then what's the next obvious one? I think the next obvious one is this one. I think this one. Okay, so you like you have, so Rn plus 1 minus 0. So it's homotopy equivalent to Sn. And then once you homotopy equivalent to Sn, then you are just identifying the antipodal point. Okay, antipodal point. Okay, because you already make the whole line into 2 points, and then these 2 points have to be the same because you regard the line as. Okay, and then next one is a bit challenging. I think we should go to this one. This one a bit challenging. How is it true? This one. I just take half of it. I just take half of it. Hey, this one actually you are also familiar actually. Huh? Yeah, no, not quite the same, but I think we saw this picture before. I think we saw this picture before, right? From where we can straight away see this picture. So if let's say we do the one for R2, okay, let's do the one for R2. And then we identify this line as point, right? Okay. Yes, we take half only. Okay, so we just take half of it. And then I identify these 2 points here. Okay, why? Because the whole line we regard as one. Okay, so this is how we get this hemisphere. Okay, and then we identify the boundary. So the boundary is that 2 points. Take those 2 points live on the same line, so they are the same. Okay. And then from there, we can go here. Okay, imagine this. From there, we can go there. Okay, imagine this. Yeah, in this case, it's D1. In this case, it's D1. No, D1 is S1. I'm sorry, D1 is the one cell. In the one cell. Oh, no, this one. This blue line here is one cell. Oh, this is D1. D1 bar. D1 is an open one, so I close it. Okay, makes sense, huh? Oh, sorry. I think we use the B notation, right? Let's use the B notation. So just use B. Actually, that means this. So B1, B1 bar. Okay. B okay. B. Did I put the wrong subscript or superscript? B. Yeah, one-dimensional ball. Yeah, it's just a line. But if B2, do you remember the calculus? Let's see. If someone type out my thing. Hey, got class me later. Well, if I have algebraic topology class notes with me or not. Main geometry. Where's the picture? Projective. Projecting space. Yeah, this one. Okay. So this one is the picture we had just now. Okay. How about this one? This is like here, right? And then here. Okay, so this part is like the D2. Sorry, B2. Okay, B2 bar. And then on this boundary, we identify with the antipolar point. Okay, so this is actually this is topologically RP2. Okay, so topologically RP2 is like a cap. And then with this boundary identified, it's antipolar. Identify because on this circle, right? You have to identify the 2 points on the same line. Yeah. Okay. So RP2 actually is a cap with this boundary identified with its antipolar point. And connect. And this is just part B2. I mean, what it means? B2 is this right? Yeah, B2 is this.
This way.
Yeah, B2 is this. This is just like this, but doesn't happen. Okay, makes sense. Or question? Okay, so similarly on this one is the B1, right? It's a one cell. So here is a one cell. Okay, here is the two cell. Okay. Yeah. Two cell with antipolar point identified. And then the other one is one cell with also the antipolar point identified. Those on boundary, those are on the boundary get identified. Okay. If you are not on the boundary, you stay as yourself. Okay. A question? Okay, so if we have this, so what do we have? So we see that there's some CW complex structure here. So how do we deal with this? Okay, so let's quickly finish it. So from here, what do we see was actually RPN. Okay, RPN is obtained from RPN minus 1 by attaching an N cell via the quotient projection here. Okay, so how do we see this? I think we should see it from this last one. Okay, this last one is important here because this BN here is the N cell. Okay, this Bn is the answer. Okay, so if you are like RP1, okay, if you are in the RP1, then you are doing what? You are using one cell to attach. Okay, if you are RP2, you are using B2 to attach. Okay. Okay. Once identified, you will get the smaller RPN. Okay, this is the same decomposition we get in algebraic geometry. Okay, you can split your RPN into RP1 with some with RP. Okay, let me show you this. Is decomposition here. Where's the decomposition? 下面一点点有，还是上面？RPN decomposition. I think, yeah, I think it's a, yeah. Thank you. So it's this one. Yeah. Here, this one. Okay. This decomposition here. Okay. Yeah. Okay. If you are not familiar with this one, you just do it step by step, using the argument in this algebraic topology. Okay, you just use this step by step. And then by induction, you'll see that RPN has E0 up to En. Use En, you identify opposite. Then when you identify the opposite one, actually is the structure of the smaller RPN. Okay, then you can keep doing induction up to the E0. Okay, E0. Okay or not? Yes. Sorry. Which one? This one. This one, why? I think you need to write down the homeomorphism. I think there's one way. I think this is the other way. Wait, let me think. Yes. Higher is a higher, yeah. But this one is a bit different. I think this you should be able to write down the homeomorphism for this. Yeah, you should be able to write down the map. Yeah, it's you should think about it as gluing for now, but I guess for this case, yeah. Okay. Any other question? Any other question? Maybe we can resume from here next time. Okay, so see you next week.